Good day, dear audience. I am Jaime Riascos and I will talk about our research paper Aphids detection on lemon's leaf image using convolutional neural networks. So this is the outline. We will introduce you the topic of this research with its related works. Later on I will present you the materials and methods used in this work. Finally, I show you the main findings and discussions with their respective conclusions. Citrus, especially orange, lemon and tangerine, are among the essential fruits plants worldwide. Its cultivation and consumption are carried out equally in the 5 continents, being exploited commercially in all countries where the climate conditions are optimal for its development. Focusing on lemon plants, they are affected by a large number of pests, which produce considerable losses in the quantity and quality of their productions. Aphids are among the most destructive pests of lemon plants. They are small insects that suck plant sap and affect the crop growth. In the image, we can see an example of aphids for lemon plants. To have an idea about the magnitude of the problem, in Ecuador in 2016, lemon production decreased mainly due to the presence of aphids. Currently, the traditional method of aphids detection is to identify the small insect manually. Early detection and identification of lemon plant disease is necessary to minimize the loss of plants, for better treatment and preventing the spreading of the disease, and in this way improve the crop production. Therefore, more advanced and sophisticated methods should be used to support the aphids detection on lemon's leaf. In this sense, machine learning emerges as an alternative that plays a dominant role in plant disease detection and identification. In this area, especially, we have convolutional neural networks, which are the current state-of-art architecture for image classification tasks. In citrus plants, aphid detection words are scarce, but in few cases, CNNs have been employed successfully. For example, in this work, Shin and colleagues exposed a method for segmentation and counting of aphids nymphs on leaves. They achieved a precision of 96% for automatic counting of aphids using CNNs. On the other hand, Xu Song and colleagues used a contour detection method to real-time enumeration of aphids through smartphones. They achieved a counting accuracy of 95% and 93% for greenhouse and outside scenarios, respectively. Finally, Shin and Lee compared several CNN architectures to classify 10 citrus pests, but aphids is not included in this study. The model used in this study reached in average an accuracy rate between 94% and 98%, although the words mentioned above have demonstrated to be adequate to carry out citrus plant disease detection, they present some issues that should be tackled. Firstly, no studies have focused on the automatic aphids detection from lemon leaf image in real conditions, such as background with multiple lighting brightness. Also, it's important to study the adequate selection of parameters in CNN architecture, since a poor choice can lead to a performance degradation of the neural model. Thus, in this paper, we propose a CNN-based approach to classify lemon leaves regarding whether or not aphids are present. In our approach, we adopted the BGG16 architecture and modified the pertinent weights to fit our model. Also, we analyzed the influence of unfreezing layers techniques and compared this approach with machine learning techniques. Classification problems have been considered a key component of machine learning. with a huge amount of application in diverse areas. A classification problem can be formally defined as the task of estimating the label y of a key dimensional input vector x. So the aim is to use the input data to train the model in a supervised way for separating the classes and predict the label for new data. In this work, we tackled the detection of aphids on lemon leaves as a binary classification problem. For this study, we created our own dataset. The images of leaves were taken from a lemon crop located in Junín, Ecuador. We captured the data for 2 weeks in order to obtain several real conditions, such as multiple lighting brightness and temperature levels. The images were captured by using a smartphone camera with a reasonable resolution. We captured 150 images, where 70 were healthy and 80 with aphids. We carried out an annotation process using label bots. Finally, we put our dataset available in Mendeley. In this work, we used the BGG16, a pre-trained CNNs, to tackle the detection of aphids on lemon leaves as a binary classification problem, analyzing the whole image without applying any segmentation process to the same. The BGG16 is composed by 5 convolutional blocks, followed by a flattened layer that is the input of the fully connected layer with ReLU activation. The output finally is connected to a 2 hidden layer neural network with softmax activation in order to predict the presence or not of aphids. We consider the well-established measures such as accuracy, precision, recall, also known as sensitivity, and F-score. Moreover, we include the ROC curves to compare the performance of our approach with other classification methods. Here we consider the aphid presence as positive and the healthy leaf as negative. Our CNN model was implemented by using ARC with TensorFlow library and Keras framework. The support vector machine and random forest algorithms used for comparison were implemented using scikit-learn. Based on the default setting for binary classification, we performed our CNN approach with the following parameters. Firstly, the number of iterations was 30, the number of epochs 50, the batch size was 32, the optimizer used was Adam, the learning rate was set up in 0.0001, and finally the loss function was gross entropy. We carry out a preprocessing stage to adapt the input images properly to the experiment. Firstly, we resize the image from the input resolution to 100 pixels. Later, we used a rescaling factor in order to normalize every pixel value. We split our data in 3 subsets: training, validation, and test. Finally, in order to reduce the overfitting during the model training, we used data augmentation to increase the size of our trained subset. Initially, as a result, we showed the influence of unfreeze early layers. The weights of BGG16 are pre-trained using the imagined dataset. To evaluate the ability of this neural architecture to detect aphids on lemon leaf image, we performed a fine-tuning process by unfreezing the convolutional layers available in the blocks. Visually, we can see that the first layers, until the layer 4, present a major variability in the 4 metrics. For A, we have accuracy, for B, the F1 score, for C, the precision, and for D, the recall. And this variability is reduced in the last layers. Here we can see numerically this variation, using pre-training weights of BGG16, in other words, when none layer is unfrozen. The CNN achieves values between 0.50 and 0.85 in the four classification metrics considered. When the convolutional layers of the two first blocks are unfrozen, the performance of the CNN is like the previous case. However, from block 3 to block 5 can be observed that unfreeze convolutional layers to reduce the weight of CNN seems to improve the performance. Results showed in previous figure and this table seem to demonstrate that, at least visually, the performance of the network improves when the layers are unfrozen from block 3. To prove it statistically, we carry out ANOVA tests demonstrating the statistical significance of the CNN approach when the third convolutional layer in the fourth block is unfrozen. This case has the best average value in the four metrics considered. These findings indicate that to unfreeze layers from convolutional tree in block 4 has a positive effect in the CNN performance. To demonstrate the advantage of our CNN approach, we compare it with SVN and random forest, which are techniques commonly used in image classification. Our approach obtaining the best mean values showing a sensitivity in recognition of positive image, it means Aphids, equal to 70%, while concerning the ability to identify the negatives, it means healthy, it showed a specificity of 74%. Note that SVN also has an excellent performance for Aphids detection, it means sensitivity, with it also degraded when healthy leaves should be detected. From the comparison of our CNN approach with the other classification methods using the same dataset, the potentialities of the method for the detection of healthy leaves and leaves with the presence of aphids can be deduced. An 87% of accuracy implies that globally our CNN-based classifier is doing a good job identifying aphids on lemon leaf images. Here we can observe the rock curves with the AUC values. We can see that the AUC value for our CNN approach is higher than those of other classification methods. Visually, it seems to have the best performance for image classification. Thus, we conducted a statistical test and found p-values lower than 0.05 when comparing our approach with SVN and VGG16. So we can say that there is a statistically significant difference between these methods. However, when our CNN approach is compared with random forests, we didn't find any significant difference. Using our best CNN approach, it is possible to classify 9 out of 10 images of lemon leaves evaluated. In this sense, the precision and accuracy metrics that answering the questions what proportion of positive or healthy leaves identification was correct and what percentage of predictions, it means healthy and aphids, was correct, achieved a 90% in both cases. These values indicate that our approach can detect aphids on lemons leaf image with a high performance. As a conclusion, we can say that we were able to design a CNN approach for aphids detection on lemons leaf images. It is based on the VGG16 pre-trained network architecture. Also, we demonstrated that unfreeze a convolutional layer in the block 4 to fine-tuning the process of weight update contributed to better predictive capacity of our CNN compared to original VGG16 architecture. The results show that the CNN approach achieved average between 81% and 97% of accuracy, F-score, precision, and recall for the binary classification problem. A statistical test demonstrated that the proposed CNN approach could detect aphids on lemons leaf images with higher levels than other machine learning methods. As a future work, we expect to continue with improvement of our approach, considering multi-class problems and implement it in large-scale pets detection in our countries. Thank you very much for your attention, and you can write us for any question.